I'd like to just remind the speakers they must stand right in front of this microphone or the webcast will not capture their comments. Questions should be asked with microphones, and if that doesn't work, we'll have to have the speakers repeat the questions. Now, Clive Schiff, my neighbor in the Institute, will be the moderator for the first sessions. And Clive has seen malaria longer than any of us and has such interesting perspectives. I thought he was the perfect person to lead this program off. Clive, could you join us?
Good morning, everybody. It's a great pleasure to do this, to introduce to you Dr. Malla Rao from NIH, because he's the heart and soul of the ICEMR project. And as Dean Clegg was talking about fieldwork, this is the strength of the ICEMR project. The beauty of this, it was funded for 7 years. It had the ability to get into the real problems of malaria. I'm talking about the real problems to people who work in laboratories, but in fact the real problems are in the field. And so much has been discovered by these ICEMRs. The ICEMR concept, Malla, is magnificent. It's something to be very proud of, and it's a debt, actually, that the malaria community owe to you. Thank you for all the hard work you've put into this.
Thank you, Clive. First, I'd like to thank all the organizers for hosting this symposium, and special acknowledgement to Dr. Peter Agre for his stewardship and championing the cause of global malaria control and elimination. So when we were, about 8 to 10 years ago, when we were actually conceptualizing the ICEMR program, we had noticed that much of the research that was taking place was very compartmentalized. You had people doing genomic research, immunology, vector biology, but each was very focused in that area of research that the grant was funded to do. So we thought we needed to take something which is much more broad-based, multidisciplinary, and take an integrated approach to doing malaria research. The idea being you collect information at the molecular level, how it plays out within the human, the host-parasite interactions, then up to the individual level, population level, and the whole ecosystem. And the idea being here that you integrate and take a very holistic approach to the research with the idea that it is actually going to inform surveillance strategies, translational research in terms of new product design, as well as ultimately lead to new interventions. So you're going to hear a lot more about all these areas and the various ICEMRs and what they've done, so I'm not going to dwell a whole lot on that front. Typically, when people think of product development and translational research, they develop a product in the lab, take it to the field, evaluate it, and if it's not performing well, they go back to the lab and get the second generation of products. The problem with that approach is unless you take the observations from the field and inform your product development process, you're really going to fall short, because it's the realities in the field that really should be informing your next generation of product development. So in this paradigm, the ICEMRs have made quite a few inroads. You'll hear the details again later on, but the fact is parasite diversity and mix in the field should really be informing the next generation of your arrays, be it protein arrays or SNP arrays or what have you. So using a reference 3D strain protein array in West Africa is going to have very limited utility if most of the strains are of a different origin out there. Taking RDTs, the rapid diagnostic tests, there have been observations in certain field areas where the RDTs have limited value because most of the parasites there are HRP2 and HRP3 negatives. And these RDTs are based on the HRP2, HRP3 antigens. So we have to go back to the drawing board and see what we need to do to develop new RDTs. You'll hear a lot about vector behavior, that vectors are now biting outdoor and more biting earlier in the evening. that sort of impacts the effectiveness of bednets and IRS. So you've got to go back and think of new strategies of implementing new control measures to address this emerging problem. So this ICEMRs have been in the field for 7 years. They've collected a lot of data. And in this day and age, terabytes of data are there in your laptop. Now you're thinking of petabyte, exabytes, and zettabytes. Just to give you a little bit of a feel, 42 zettabytes can store all human speech ever spoken. And we now have the capacity to store such information. Now, when we talk about big data, people are of the impression it's huge volumes of data, and all we are trying to do is mine the data. And that's not quite what big data is. So in the few slides, I'll just give you a little bit of an introduction on what big data is all about. So the big data framework to the right, you'll see that the picture, which probably have seen in many illustrations, these are called commodity clusters. And what commodity clusters are racks and racks of disk storage. In addition to it, there are racks and racks of CPUs, processors. In the conventional framework of doing large-scale data crunching and number crunching, we used to have these supercomputers, the Cray XMP, the Cray YMP. What you used to do is get the data to the central supercomputing facility, crunch through these complex models, complex algorithms, and come out with your answers. But this day and age, you cannot take that paradigm, because if you try to move zettabytes and petabytes of data, the process of just moving the data to the supercomputing CPU clusters are going to be so huge that you're wasting time more in the I/O process. So we have this new approach, which you'll hear quite a bit in the modern day age, is MapReduce engines. The strategy here is, instead of getting the data to the central computing facility, you move the data to the computing facilities. So when you have lots of computing facilities like these commodity clusters, what you do is you move the data to the clusters. And so you'll see these slaves out there. These are called data nodes, where there's lots and lots of data storage there. And you have redundancy. Each copy of the data will be sitting on many, many clusters, and each one will be cranking asynchronously all your algorithms there. At the end, it goes one step up, gets reduced, shuffled and sorted, reduced, then gets one layer up, and then goes to the application clients, and then presents the output to the clients. So that's the paradigm of the big data framework. Now, another word you'll hear a lot in the big data framework is Hadoop. Hadoop is an open source, publicly available software system. And this was developed by two people, Doug Cutting and Mike Caprella, after a white paper was put out by Google on the MapReduce approach. And you'll see Hadoop always has this yellow color elephant. Hadoop was named after Doug Cutting's kid's stuffed toy elephant. That was the name, Hadoop. So you see, everything is Hadoop. Now you see a lot of this big data has taken off in the last 3 to 4 years. And most of it is open source. So you'll see names like Pig, Impala, Giraffe, Hive, Mahout, all like the Animal Farm sort of software modules there. And you have the Zookeeper, which makes sure that everything is operating in a proper fashion. So at the base of Hadoop, you'll see what you call the HDFS, which is the Hadoop Distributed File System. This is what I just explained to you, that they are distributed in so many clusters and so many copies of it, such that if one cluster went down, a backup copy immediately comes up. And the next layer, you'll see Yarn MapReduce. That's the engine that actually controls distributed processing. So that, again, it's a fault-tolerant system. If one of the clusters goes down, MapReduce will make sure, the Yarn will make sure everything kicks in the right way. And then you have these layers, and you really need not to worry about all these layers, because you'll be working right on the top, which will be the application and presentation layer. So to give you a little bit of an example of how big data is implemented, and probably most of you have used Google Traffic, and you see these little bottlenecks where the red lines are. How do you think Google Traffic operates? Behind the scene, it takes data from various sources, the satellite maps, the satellite images. aerial systems, traffic cameras, traffic signal lights. But the most important thing which people don't realize is those cars out there. Every cell phone sitting in a car, though you're not speaking on the cell phone, is actually transmitting a signal to a control tower, cell tower. And the rate at which the signal is moving is the rate at which the car is moving. And that gets combined with the historic traffic patterns, with all these other various sources, and in a fraction of a second, relays back to you on your cell phone where the traffic congestions are. That's an implementation of big data. Now, big data in epidemiology. Most of you might have heard of read the paper on the use of cell phone to track movement of people. And they overlaid it with malaria cases in various clinics, and they tried to track how malaria was spreading. Another implementation was a few years ago, they combined travel data with flu occurrences in the various parts of the world and traced the flu epidemic to have come out from Mexico and not from China, where people think it always originates. So that's another big, huge implementation where they took tons and tons of all the airline records and combined with clinical data. IBM has developed a big data implementation called Spatio-Temporal Epidemiological Modeler, which has modeled dengue with 55 differential equations, multiple compartments, and lots of maps and all that. One of the limitations of this approach is that it gives you a lot of very good, important information, but everything is what you've observed. You've collected data from the past, you've assembled the maps from the past, and you put everything together, and it gives you a lot of valid information, and it tells you the story. But what it does not tell you is, what can I predict in the next few months or the next 6 months or next year? What I've observed today, what is the validity or how useful is it going forward in time? So when it comes to malaria, we have a lot of so-called established interventions, and we have quite a few, what, for the lack of a better term, I said emerging control measures, but these are not yet widely implemented in public health practice. The big question is, what is the optimal mix of interventions? And do you have to have a different set of interventions in different settings? In other words, when we have a very high transmission area, what would be the mix of interventions? When you have something which is very low transmission, or something in between, like epidemic or declining or re-emerging infections. The bottom line here is that you have to measure impact assessments. And the impact indicators would typically be on the vector side or on the human side. On the vector side, you would typically think again of vector abundance, EIR rates. On the human side, you try to measure clinical disease in terms of morbidity and mortality and asymptomatic reservoirs. But in between, to get the real true perspective of what's going on and the complexity of the disease and transmission, you really need to measure parasite diversity, emergence of drug resistance, insecticide resistance, immunity of the population, the shift in severity and age distribution of the population. So there's a lot of other research measures that you have to be measuring constantly in this framework. Anyone who's done, and I'm sure many of you out here have done phase 4 studies, these are huge trials. To do these type of studies where you have to take a mix of interventions, you nearly have to implement cluster randomized trials in large areas to the order of 500,000 people to 1 million people. The whole process of just taking the classic approach, if you were just to do a census of these places, it can take 3 to 5 years just to do a census of 500,000 people in a very rigorous way. To set up surveillance in 50 to 70 clinics takes a long time. So if the whole project, which can take 5 to 7 years, you spend $20 to $50 million in these huge things, and then you come up with an answer, how good is it if things have changed in that time frame? Incidences have changed, the interventions have changed, control programs have changed. So you really have to rethink the whole paradigm of how we're going to implement these more pragmatic, large-scale intervention studies. So here's what I'm thinking of, and this is my vision. On the left, you have, as I explained to you, taking the big data model you have a huge amount of open source software implementations, portals with large amount of data. You can get data on remote sensing, genetic sequences, and there are knowledge engines. NoEng is one of the engines that is really designed and implemented for genomic processing. And then you have engines like Spark, which can actually handle streaming data. If you want continuous weather data coming out from weather stations, satellites, there are actually these big data engines that can handle all that. Now, you get all these data sources. Most of them are open source. You can easily write this little software and then get those streaming into your centralized big data implementation. And then you have two very new powerful tools there. One is big data analytics, and the second is deep learning. So big data analytics has really implemented some very sophisticated new compute-intensive procedures. For example, you can use the latent class Gaussian random effect field models. What this does is actually takes imperfect data where there's noise and tries to sort of smoothen that noise and get the maximum signal strength out of it. You have now new methods called synthetic likelihoods, and they implement the Monte Carlo Markov chain type of implementations in the Bayesian framework. You take the Bayesian priors, and then build these huge models, again, which are very huge compute-intensive exercises. You have what we call the adaptive spatial sampling method, which is taking the bandit problem into approach, bandit problem framework. In that, what happens is, if you think about the old days in the Wild West, you used to have bandits attacking stagecoaches and banks. So what that approach does, it takes a lot of the parameters on how, where, when these bandits have attacked these banks, and then takes spatial data from around these areas, takes variables and probabilities, puts them into a very complicated model, and then tries to predict where the next attack is going to be. So using that approach, you really can now go to prediction. You're taking the knowledge base there, and then you can enhance prediction. The second very powerful tool there is deep learning. Deep learning is what artificial intelligence and expert system was about 5 to 10 years ago on steroids, essentially. What deep learning does, it still implements the neural network framework, but the number of nodes can be millions of nodes, and the connections between the nodes runs in the billions. A classic example of the neural network, the deep learning algorithm that was actually implemented was the recent DeepMind implementation by Google called AlphaGo. And if anyone has followed that, there's a very recent article couple of months ago in Nature, which actually explains how the DeepMind was used to implement AlphaGo and play the Go game between Lee Sedol from Korea, the world champion, and the computer. The amount of combinations in the AlphaGo game equals to the number of atoms in the universe. That is how extensive and impossible that game is to fathom computationally. But in the first 3 games, the computer won. The world champ resigned. Here's an interesting story. On the 4th game, move 78, Lee implements a strategic move called the Hand of Heaven. And the computer resigns after a few moves because it doesn't know where to go. And the computer starts making random choices after that. Then what happens? Game 5, if you read that article, it says no hand of heaven could help this guy because it quickly learned and adapted itself and beat him in the next game. So 4 out of 5, DeepMind won. So this has really moved to the next level. It's an extremely powerful methodology. In the old days, when you implemented expert systems, you need to have knowledge engineers who define the rules, populate the expert system. You needed to have the computer programmers who could implement these algorithms. And together, after they implemented the whole knowledge base, they had to train it, and then it had to learn. You don't need to do any of that stuff now. You have MLlib is a deep learning engine that's there. IBM has Watson now incorporated into the ERP models. And they're using business intelligence, using deep data approaches, big data approaches, to actually start giving the ERP and the corporate world advice on what's the usage pattern, where are the inventories, what's happening. It builds beyond just the traditional database approach. Now, the next thing is adaptive design. Going back to my explanation of these phase 4 studies, I don't think we should be thinking in the conventional mindset of trying to go to 500,000 population, this traditional approach, randomizing them and giving them these interventions and following them up for 5 to 7 years, because everything is changing and probably your data has limited value at the end of the day. You have to take these more complicated adaptive designs, which incorporates some of these big data analytics and these deep learning approaches, where you can actually build as you go, sort of pick which site, what mix of interventions, get more information, then let the sort of big data approach tell you where next to go, move, and what package of interventions. So there are very sort of many innovative ways to now approaching this whole problem of large-scale epidemiologic studies. And my vision for the ICEMRs is to take such approaches from now, such that because we have what I call in those two in-between layers, all the basic science observations in terms of parasite genomics and diversity and all that stuff, to now layer on big clinical trials, leveraging all that. And I don't think it's going to be possible for a single PI or a couple of PIs in a single area to be implementing these large-scale studies. What we need to do is layer on in the next decade with all the ICEMRs, the next phase 4 studies and to answer the big practical and pragmatic questions. Just to wind up, a couple of weeks ago, NCI, the National Cancer Institute, had a huge workshop at MIT or someplace in Boston, which they call the hackathon. And what they did was they got all the people from the domain knowledge of cancer with all the big data hackers, got them there and spent a few days. They opened up the TGCA, which is the Cancer Genome Atlas. Through this portal, they get access to clinical data, cancer data, registries, environmental exposure data, and it ties into the cancer genomes, and they want to take a big data approach to how to solve cancer problems. I think we have the malaria domain knowledge here in this room. We really need to engage the IT people, the big data people, the sophisticated statisticians who have experience with these new adaptive approaches and designs, and really take it to the next stage. Thank you.